No.
Okay, so first section we're going to look at in chapter 5 is on exponential functions. There's two functions we're going to look at. We're going to look at exponentials and logs, and they're basically opposites of each other. Exponentials grow really fast. Logarithms grow really slow. So they're opposites. So I want to look at the difference between these two. I have x squared and 2 to the x. It's kind of like I flip-flopped the exponent and the base. When we're looking at x squared, Joe, what's the base in x squared?
X.
Yep, and the exponent?
Squared.
Which is
2.
2, yeah, squared 2. Good. Now in the other expression, 2 is the base and x is the exponent. One of these is an exponential type expression, one of them isn't. Okay. So the one that's not an exponential is a quadratic. And that's the one that's on the left. Okay. Whether I made it x to the second, or x to the third, or x to the fifth, anytime that the exponent is a number, that's an integer, and positive, it's a polynomial. Okay? Specifically, that's a quadratic polynomial. So when you put the variable in the base and you make the exponent a non-negative integer, that is a polynomial. And sometimes it's more complicated, like x squared plus 6x minus 7, but we're just looking at like a single term. When you start putting exponents as the variable, then we can get into things that are not polynomials. Are they always exponential? No. Depends on, there's a restriction on what the base can be. Okay, the base can only be certain things. The one that I put here, that is an exponential. Okay, 2 to the x is exponential. In fact, it's exponential doubling, something doubling over time. And towards the end, we're going to look at a formula that has 2 to a power in it. If you did 3 to a power, that would be like something tripling every so often, every minute, every hour. Okay, so when the variable is an exponent, if the base is a positive number not equal to 1, that's an exponential function. Okay, so we'll see that a couple times today. Base, positive number, real number, can't be imaginary. Positive real number, but not 1. Well, let's look at why not 1. Well, what if I wrote this? 1 to the x. Okay, I got a variable that's an exponent. But why wouldn't that be exponential? 1 to the x. Yeah, Lucas?
Because 1 to any power is always 1.
It just stays 1. It's actually a horizontal line. That's not an exponentially increasing or decreasing at all. Okay? 1 to the 50th power just means 1 times 1, 50 times. Still 1. Even to the 0 power. 1 to the 0 power, still 1. All right. So 1 to a power doesn't work. So that's why it can't be equal to 1. And I also say it has to be positive. If it's negative, we start getting really weird things that happen. Like, let's say you tried to do this. That's definitely not exponential. If I made a table, if I plug in 0 for x, what's negative 2 to the 0 power? Yeah, 1. Anything to the 0 power is 1. So that's a point on the graph. How about negative 2 to the first power? Yeah. Negative 2. Now let's do negative 2 to the second power. Yeah. 4. So when you take a negative number to an even power, it becomes positive. A negative number to an odd power is negative. So think about how you would graph that, right? It's like bouncing back and forth between positives and negatives, and it's doubling each time. If I stick with these x values. So 3 would be -8, 4 would be +16. So it's like it's just bouncing back and forth. That's kind of weird. What gets really weird too is if you start using decimals. So you try a half. What does that mean when you raise something to the 1/2 power? What's that the same as we said yesterday? Yeah. That means a square root. So -2 to the 1/2 power means this. What's the square root of -2? Yeah.
Wouldn't it be I to the square root of 2?
I times the square root of 2, it's imaginary. So when something comes out imaginary, we can't graph that on the real x and y axis. It's imaginary. So 1/2 on the calculator, you'd get an error. In fact, any fraction with a denominator of 2 would give you an error. Like if you tried to raise -2 to the 5/2 power, that means this. -2 to the 5th, and then take the square root of it. Okay? So the way I remember it is I kind of block that part out and I say, oh, it looks like -2 to the 5th, and then whatever you divided by, that's your root. Well, without even doing it out, what's a negative number to an odd power? Yeah.
It's an odd number. It'll come out to an odd number. A negative, sorry.
Yeah, it'll come out to a negative. So any negative number to an odd power is negative. But then the square root of a negative, can't do it. So any fraction that you could write in simplest terms as a denominator of 2 would not be a value you could use. But then other fractions you could. So it's just a mess. So you can't, and if you try graphing that, you won't even get a picture on the screen. It does nothing. Doesn't graph it at all. So make sure your base is positive, but not 1. So let's think a little bit about the domain. If you give me a number, again, fitting this criteria, that a is not 1, but it's positive, is there any restriction on what number you could use as a power? Like if I had something like this. Is there any power you are not allowed to raise the number 2 to? What do you think, Sebastian?
No.
No, there's no restriction. You can raise 2 to a positive. Just try it on the calculator. Do 2 to a positive number. That works fine. 2 to a negative number. That's fine. 2 to the 0. That's fine. 2 to a decimal. 1.6. That's fine. You can raise it to positive, negative fractions, or decimals. So the domain is all real numbers. Now again, remember, just a reminder on what the base is. It's a positive real number, but it's not 1. Okay, so with exponential functions, the domain is always all real numbers. Now, what does it really mean? Like I did 2 to the -5th, and I got an answer of 0.03. What does that really mean? If you had to explain to somebody what it means to raise something to a negative power, how do you do that? Or how would you write, like if I said to you, like in Algebra 1, rewrite with positive exponents. How would you write 2 to the -5th as a problem with just a positive exponent? Yeah?
You would put it as the denominator over 1.
Okay, so you'd put it as a denominator. So what would be in the numerator?
It would be 1 over 2 to the 5th.
Yeah. So 2 to the 5th is 32. And if you take 1 divided by 32, you're going to get 0.03125. So anytime you see a negative exponent, it just means it's in the bottom. Now, let's say I make that negative number even bigger, 2 to the -10th. I'm going to get an even smaller number, 0.0009 0.0000976. It's getting smaller, but it's not ever going to be able to reach what number?
0.
It'll never reach 0. I don't care if you divide 1 by 1,000,000,000. It's still not 0. It's small, but it's not 0. So when we talk about the range, okay, the range of just the basic function, if you don't shift it or move it or do anything to it, the range goes as low as 0 and up to infinity. It can go as high as you want. Think of like 2 to the 50th power. It's huge. 2 to the negative 50th power, very small. These are all examples of exponential functions. F of x equals 10 to the x, g of v equals 4 to the v, h of x equals pi to the x. They all have variable exponents. They all have positive bases that are not 1. Let's look at some things that are not exponential. Under the non-exponential, how come f of x is not exponential? I mean, x cubed, that goes up pretty fast. Why isn't it exponential? Well, Brandon, what do you think? Okay, what should the base be if it was exponential?
A real number.
A real number that's not just any real number. We have to restrict that.
Integer.
We don't have to restrict it that much. Well, yeah.
It's greater than 1.
I don't think I wrote it. It has to be greater than 1. Kim?
Positive.
It is positive,
It's not one.
but it's not 1. So it can be 0.5. Okay, it can be 0.6, 0.7, things like that. It just has to be positive, but not 1. Well, that's a variable base. No, variable bases aren't fixed, they change. So that's not exponential. G of x is pretty much the same thing. If you think of it as like 1/2 x to the 4th. It's a variable base. And then the last one, y equals, it's kind of like a hybrid of two things mixed together. It's kind of like a rational function, because it's a fraction. And you have a polynomial in the bottom, but the definition of a rational function is you also have a polynomial in the top. That's a radical function in the top. So there's really not even a name for what y is. But it's not exponential. So let's look at the difference between 2 to the x and 3 to the x. Before I graph it, does anyone have a guess what the difference is going to be? They're both exponential. But they're not going to look identical. They're going to look different. Yep.
3 is going to go up more because tripling something is bigger than doubling something.
Yeah, the rate of increase on y equals 3 to the x is going to be faster than the rate of increase on 2 to the x. At least if you think of numbers bigger than 1. Think of, like Robinson said, if you square something like 2 to the power of 5 versus 3 to the power of 5. Well, 3 to the power of 5 is much bigger than 2 to the power of 5. Right, so let's graph it and see what we get. So 2 to the x, 3 to the x. Let's start with zoom 6. And I think this will show kind of the big picture. So it starts out very flat, and then it curves up. And then the red one starts out pretty flat, but it curves up sharper after a certain point. Okay. If I zoom in, let me zoom in a little bit, and I think you'll be able to see something happening. So the red one curves up sharper after you pass what? Yep. Okay.
After they set, or after it passes through the y-axis.
Yeah, after the y-axis, after you get past x being 0, then the cubed one takes over and starts going up faster than the blue one. But before that, the blue one is actually on top of the red one. So they switch places right at the y-axis. Okay. Any question on that? So it's kind of weird, but if you take a number smaller than 1, squaring it is actually bigger than cubing it. Right? Which we know that's the opposite when you get numbers bigger than 1. Okay, so smaller than 1, squaring is bigger than cubing. Larger than 1, cubing is bigger than squaring. Exactly 1, well, they're the same. Doesn't matter if you take 1 to the 2nd power or 1 to the 200th power. It's still always going to be 1. Okay? So I just kind of wanted to look at those and see the pattern. The other thing they're going to ask us to do is compare graphs that have negative exponents to graphs that don't. Like this one. It's a lot easier if all our graphs just have positive exponents. That makes it much easier to work with. So what does a to the negative first power mean? If I wanted to write that without a negative exponent. How about, see? Do you know what that means if you raise something to the negative 1 power? We kind of did it with like 2 to the negative 5th. I think Kim or somebody had told us what that meant. No, I think he told us what it meant. So yeah, 1 is going to be in the top, and what would be in the bottom in this case? We have a to the negative 1.
It would be a to the first.
Just a to the first, or we could just write a. So we can use that to simplify something like this. A to the negative x. Even though it's not written, what number is in front of that x? Joe? There's a negative 1 in front of it. So if I want, I can put it in like that. It's negative 1 times x. That's negative x. Now, you've got an exponent right here, and you multiply 2 things together. When do you do that? When do you multiply exponents together to get an answer like that? Yeah.
You have a power to a power.
Exactly. You have a power to a power. So the way you can think of that, think of it as a power to a power. A to the negative 1 times x is a to the negative 1 to the x. Power to a power, you multiply those together. And that will bring you right back to what we started with. Well, the reason I wrote it that way is because now we can make a substitution. A to the negative 1 is just 1 over a. And the x just stays right where it is. So the shortcut, when you're raising something to a negative power, you can get rid of the negative as long as you take the base and flip it. Right? So if I had something like 2/5, and I wanted to fix that, okay, I didn't want it to be a negative power. All I have to do is flip the base, and then I can just keep the exponent the same. In this case, it's just to the first, so it doesn't make a difference. But if it was like to the negative 2nd power, I would flip the base and make the exponent a 2. Okay. Any questions on that? Okay, so let's use that idea right here. I want to find complete graphs of 2 to the x and 2 to the negative x. Now, this isn't necessary, but it's going to help me to make another point after this. How can I rewrite 2 to the negative x? So there is no negative exponent there. Yeah. Exactly, 1/2 to the x. And what I'm trying to point out is you're going to notice a very big difference between f of x and g of x. And it all has to do with the base. Okay? There's a number that controls whether the graph is going to increase or whether it's going to decrease. And we'll try to figure out which one is which in a second. When you type these in, it doesn't matter which version of g of x you type in. Either one. So I got 2 to the x, 2 to the negative x. Let's try 2 to the negative x. Now, the other way you can think about this too is think of it as a transformation. This negative is inside the exponential function. Whenever we do stuff inside, that's a horizontal. If I put a negative on the outside, that's vertical stuff. What does a negative cause the graph to do? Yeah. It's going to flip over an axis. When the negative is inside, just like when you do anything inside, that's a horizontal. A horizontal flip means left to right. So this is going to flip over the y-axis. So we should see mirror images of the same graph. Let's see. I'm going to zoom out a little bit. Let's go zoom 6. There's 1. There's 2. So algebraically, just by looking at the negative, that's what I would expect. I would expect a mirror image, and that's what I got. Let's look at the domain and range of each of these. Okay, so f of x was the graph in blue. G of x is the graph in red. F of x, G of x. So let's start with the domain of the graph in blue. How far left and right? Henry, how far left and right does that graph in blue go?
I'm not sure.
It's okay. Anyone help him out? So that's the same as me asking what values you could plug in for x in this formula. What values can you raise the power of 2? 2. Yeah.
All of them?
All of them. So that domain of f of x is all real numbers. It's going to go right forever. It's going to go left forever. It's going up steep. So it doesn't look like it's going to the right fast, and it's not. But it still is going to the right. So negative infinity to infinity. And now let's do the range. The range is up to down. Does the blue graph go up and down forever? No. It does one of those. Which one does it do? Yeah.
Goes up.
Goes up. Goes up forever. So the range, it's going to go towards infinity. What's the lowest that the graph ever goes? Well, we already said that it never reaches it. So 0. It's going to approach 0, but it'll never reach it, because think of it, when you start heading to the left, that's a negative number. 1 over anything is still going to be a very, very small positive number. It'll never reach 0. Now, let's do the same thing for the graph in red. What's the domain for g of x? Yeah.
Negative infinity to infinity.
It's the same thing. Still goes left forever, still goes right forever. What's the range for the graph in red? Yeah.
Negative infinity to 0.
So negative infinity, so you're saying the graph in red goes down forever? I mean, it does go down, but I think the graph in red levels off. to me it doesn't look like it goes down forever. It looks like it goes up forever, but then it kind of stops. Anyone have another thought on the range? I mean, if it went down forever, it would have to look something like this. Which I could make it do. I could take the graph in blue and I could mirror image it. And then it would go down forever. Or the graph in red. I could flip it. But if I don't flip it, just leave it like that, what's the range?
Same as the other one.
Same thing. Still 0 to infinity. The graph in red goes up forever. But it doesn't go down forever. It comes down and it looks like it gets close to the x-axis and it never crosses the x-axis. So mirror imaging an exponential function over the y-axis doesn't change the domain or range at all. It does change the picture. It doesn't change the domain or range. Any questions on that one? All right. So what I want to do now is, instead of just thinking about like 2 to the x or 3 to the x or 4 to the x, I want to look at the pattern in general. Okay? So let's pretend that a is a positive real number. And also that a is greater than 1. Because if a is not greater than 1, then we get weird things that happen here. Like if a is a half, 1 divided by a half is actually 2. I don't really want to think about that. So let's just pretend a is a positive real number greater than 1 for what I'm about to show you. So f of x is kind of like the f of x I did on this page. This is a specific f of x. It's 2 to a power. This is some number to a power. Okay, so it's more general. G of x, where it's 1 over a to the x, is kind of like this one. This was 1 over 2 to the x. This is 1 over anything to the x. So it's more general. Make the graph a little bit bigger. If we look at the graph in blue, which is kind of like a to the x. I know it's specifically 2 to the x, but that's okay. We can still see the pattern. What happens to the graph in blue as you head towards infinity? As the x value heads further and further to the right, what happens to the y value? Hasten? What happens to the y value as x approaches infinity? Joe, you have a thought?
Goes up
And what does it go up to?
towards infinity.
Towards infinity. So, again, the graph of f of x, I have a to the x. This is 2 to the x. Close enough. 3 to the x, 4 to the x, 20 to the x, they would all pretty much look the same. It goes up as you go to the right. Now, again, looking at the graph in blue, what would happen if we head to the left? So if you have a number that's not a fraction raised to a power, and it's a negative number, what happens as you head further and further left?
Gets closer to 0.
Gets closer to 0. Doesn't matter if you raise 2 to a big negative number, if you raise 5 to a big negative number, if you raise 13 to a big negative number. They're all going to get closer and closer to 0. Now we want to look at what happens when we have a fraction. Right? Instead of a whole number, or a decimal, or a number really bigger than 1 raised to a power, let's look at small numbers like 1/2. 1/3, 1/4. That's what would happen with the graph in red. So with the graph in red, what happens is x gets bigger and bigger and bigger. Trish?
It approaches 0.
It approaches 0. So the graph in red would be something like, I think we did y equals was 1/2 to the x. If you take a fraction and raise it to a bigger and bigger power, it gets smaller and smaller, approaching 0. Now, if you take a fraction and raise it to a negative number, it gets huge, right? Like 1/2 to the negative 20th power, that's a huge number. It goes up, and it approaches infinity. So what do you think controls whether something is going to grow as you go to the right or decay as you go to the right? Because we have an example of each. So can we kind of summarize that? Yeah.
The base.
It's going to be the base. The base is in control of whether you have growth or decay. And what value do you think is going to be like the dividing point between, okay, if you're bigger than this, you get growth, less than this, you get decay? Yeah. 1. Yeah. Okay. So the key difference, we just summarized it. Greater than 1, you get exponential growth. Between 0 and 1, you get decay. What if the base is negative? I already told you it never will be. We're not going to do that. So any questions on that? You'll see more with growth and decay when we get towards the end of the lesson. We're going to have a few word problems about growth and some about decay. We're going to look at like general growth, like maybe a population of a city that grows at 2% each year, or you have a salary and you make 1% more each year. How much money would you make 10 years from now? Or we could also look at something specific like doubling. That's a popular, common exponential growth, like bacteria doubling every hour. Start with 100, how many would you have after one day? So, transformations on exponential functions. It's exactly the same as all the transformations we've done all year. I'm not going to write it all down. I'll summarize it quickly. When you do stuff inside a function, that's your horizontal. When you do stuff outside the function, that's your vertical. Anytime you add or subtract, that is a shift. Either left, right, or up, down. Anytime you multiply, that is a stretch. Either up, down, or left, right. Depends where you multiply. And remember, the horizontal stuff is always the opposite of what you would expect. The vertical stuff is always what you would expect. But horizontal is always the opposite. So if you remember those things, you should be able to tell me the transformations right there without too much of a problem. Whenever you're comparing exponential functions, the bases would always be the same. I'd never have you compare like 5 to the x to something that's like 2 to the x. You gotta have bases that are the same. So our bases are both 3. First, can somebody tell me how many transformations we have to turn f of x into g of x? Yeah.
3.
3. Yeah, I agree. There's 3 transformations. So I'll write them down. Now, I don't want to know what the transformation is, but can someone just tell me what number am I going to focus on first to figure out the transformation? I have the 2, the 1, and the negative 5. I just read them in order left to right. 2, the 1, the negative 5. Which one do we look at first? Yep.
5.
No, that's last. That's the very last one we do. So that's going to be stuff that's outside is always, that's going to be at the end. Yep.
The 1.
The 1. We always start inside and we always start with the shift. Remember the order. Horizontal shift, horizontal stretch, vertical shift. That's your order. So the plus 1, I agree, we're going to look at that. And what's the plus 1 going to do to my graph? It's addition, and it's inside. Yeah.
Move it to the left.
It's going to move it opposite way we would think because it's inside. So yes, it's going to move it left 1. So shift left 1. If there was a number in front of x right here, I would now be talking about a horizontal stretch. There is no number in front of x, so there is no horizontal stretch. And remember, the opposite of what you think. A big number in front of x, like 20, a big number would actually compress the graph by 20 times as much. A small number, like 1/5, would actually stretch it larger. How much larger? Well, if it was 1/5, 5 times larger. Okay, but we don't have to worry about it here. So now we go outside. So I already said the -5 is the last thing we look at, so the 2 is the next thing. What's the 2 going to do? Yep.
A vertical stretch by 2.
Yep. So that's a vertical stretch by factor of 2. It's on the outside. That tells you it's vertical. It's multiplication. Tells you it's a stretch. The last thing, it's on the outside, but it's a subtraction. So what's the -5 going to do? Yeah.
Shift down by 5.
Yep. Shift down 5. We didn't have it in this case, but what if put 2 boxes in that problem? What if there was a negative in either one of those boxes? What would that cause the graph to do? If we had a negative in there. Yeah. So
Reflect over the axis.
it would reflect over the axis. Which axis? Depends which one is negative. Inside is a horizontal reflection. Outside is a vertical reflection. So you just have to keep that straight which axis is which. Okay. But other than the reflections and a stretch horizontally, we had everything else. Any questions on that? Yeah.
Might be dumb, but why does it shift left 1?
Because the stuff that's horizontal, it just always does the opposite. So when you see plus, it brings it left. When you see minus, it brings it right. Same thing here. Compared to the square root of x, that's going to push it left 2. That's how it works. Okay, so what they're saying here is that these 2 functions are the same. I think if I showed those really quick for like maybe 1-2 seconds, and then I covered them up, people would probably say, oh, one of them was growth, one of them was decay. Because they see a base bigger than 1 and a base smaller than 1. But they're actually the exact same thing. They don't look the same because they're not set up the same. All right. Let's take f of x and see if we can rewrite it and make it look like g of x. Okay, if I had to compare these 2 functions and they didn't tell me up above that they were already equal, this is what I would do to figure out how one compares to the other. Right now, it's like you're comparing apples and oranges. They're not set up the same. So let's start with this. What's something I could do with the exponent on f of x to make it start to look a little bit more like the exponent on g of x? Something about those exponents that's very different if you look at the setup, like the format. Yep.
You could put -2x plus 3.
Yeah, we should at least set things up so, okay, we want our variables first and we want them second. Now we have a mix. So let's set it up so the variables are first. Now the next thing I look at is I say, okay, they already gave me a hint that these are equal. That means that somehow that and that are going to come out the same. So what I could do is I can factor out a number from x, but then I also have to factor it out from 3. I'm not going to worry about the 3 yet. What would I have to factor out from the x to make it look the same as the one above? Yeah, I'm going to factor out a -2, and I'm just going to hope that somehow it automatically gives me -1.5. If it does, then I'm on the right track. Well, -2 times something is +3. Negative times what kind of number is a positive? Yeah, it's got to be a negative. And -2 times negative what is +3? Yeah, 1.5. -2 times -1.5 does give me +3. So when I factored out the -2, I got lucky. That exponent came out pretty similar to the other one. But they're not quite the same. They're almost the same. How do you get 0.25 from what we have? Yeah.
Could you make it 1 divided by 2 to the second?
Yep. So that negative exponent means it's really 1 divided by 2 to the second. This just stays the same. And now 1 over 4, that's the decimal point 25, 1/4. So we just showed that even though they look different, they are exactly the same thing. They're both examples of decay. They're not growth. Any questions on that? Okay. This is just something I'm going to show you quickly because it's kind of like a weird thing that happens and you're going to make a connection with it tomorrow. But it's an exponential function, so we'll tie it into today. I want to look at what happens as x gets really, really big in that fraction. What happens to that fraction as x gets huge? Yeah.
It's closer to 0.
Yeah, so we get 1 plus something really close to 0. And now we're going to take something that's really close to 0, we're going to add 1 to it, and we're going to raise it to a huge number. So it's kind of like we have two things fighting each other. We have something extremely close to 0, adding 1 to it. That means you've got something extremely close to 1. Well, if you take something extremely close to 1 and raise it to a huge number, what's going to happen? Because we already said if you take 1 to a huge number, it's 1. This isn't 1. It's something as close as you can possibly imagine to 1. It's like 1.00000000001, as many zeros as you want. So it's as close as you want to 1. But then it's a huge number we're raising it to. So let's just graph it and see what happens. As far as looking at it analytically, like using algebra, you'd probably do that in calculus. So we're going to look at it graphically and see what happens. It's kind of hard to predict what's going to happen without knowing something a little fancier than what we know right now. But we can graph it. And if you graph it, it looks like as you head to the right and the left, it's actually leveling off. Okay. If I put in 50 for x, I get about 2.7. If I go over to 500, I get still 2.7, a little bigger, 2.72. If I go to 9,000, well, from 500 to 9,000, it didn't change much. It went up 3 thousandths. It didn't get much bigger. And in fact, it's pretty much going to level off at that number. That number that it's leveling off at is actually the number E. There's a horizontal asymptote in this graph. And it's at a number called E. E is the number 2.718281828. The pattern doesn't continue 1828 after that. It changes. I don't remember what it is, but it changes. And the reason I'm showing you that is because when we look at section 5.4, which is on logarithms, this asymptote that happens to be the asymptote of an exponential function is the base when we study natural logarithms. So I'm trying to show you there's a connection between exponential functions and logarithms. Those are the two things we're studying this week. Again, why is it 2.718? That's not really something we're going to explain in this class. But that's what it happens to be. I didn't show you what happens if you head to the left. But if you look at the graph, you can probably guess it's still getting closer to 2.718. Both directions. Obviously, at 0, there's some kind of problem because if you plug in 0, 1 divided by 0 is undefined. So there's an asymptote at 0. Any question on that? It's kind of like a weird function. You can't really figure out what's going on if you just look at it. Like I usually say, well, just let x get bigger and bigger. What would happen? Well, you can figure out what would happen here, but you can't really figure out what would happen in the whole thing. It's too weird. It's kind of a weird one. All right, so the last thing we're going to look at is a few word problems. They're all, I think, very straightforward. You just have to plug into formulas. Now, first thing we're going to look at is for a population of a town. And we're going to assume that the population is P. There's P people in the town. So, at year 0, the population is just P. That's all it is. How would all right. So if you're growing at a constant rate, like say you get a 2% raise every year, or the population of a city goes up 5% every year, that's going to be exponential. It's slow. It doesn't go up fast, but it does go up. In year 1, how would you figure out how many people you have in the town now? Assuming nobody moved out, nobody died, everyone that was there is still there. But what would you have to add to it after the first year? Yeah? Yeah, you would have to add what you had to start with, which was, let me make this a little bigger. You still have P people, but now you have to add the growth. So it's what you had plus the growth every year. What you had plus the growth. You had P, and then the growth is P times R. So if you had 100 people and the growth rate was 2%, you'd just do 100 times 0.02. That means the growth was 2. You already had 100. Now you'd have 102. Now, I just want to rewrite that because I can factor something out. What can you factor out of P and PR? Yeah. Factor out of P. So you get P times 1 plus R. That is our new population. Okay, the population isn't P anymore. It grew. What did it grow to? What's in the red box? So now, each year I said your new population is what you had plus the growth. What are we starting with in year 2? What's our population to start with? Yeah.
P1 plus R.
p times 1 plus r. That's what you're starting with. And now, what do you multiply that population by to figure out the growth? So pretend that's 102, right? That's our new, remember I just made up an example. So that's 102 people. What would you multiply 102 by to figure out your growth in year 2? Yeah. Just a single thing. To figure out your growth, just take what you had times this. Yeah. Not a PR. So don't worry about the formula yet. I just want like kind of the general idea. So to figure out your growth, just take your population times 1 in general. Yeah. R. Just population times R. That's the growth every year. The formula for the population gets more complicated every year. The growth is still the same idea. How many people times R? How many people times R? This is how many people we have. So we take that times R. So we have 102 plus, now it's going to get into decimals. So with people, you don't have decimals. But 102 times a growth rate of 2% means you gain another 2 people and change. So we'll just say 2 people. So now you would have 104 people. Now, we looked at what we had in common and we factored it out. Let's do the same thing again. What do you have in common in this term and that term? Like if we were doing like a factor by grouping, what do they both have in common? Yeah.
P times the quantity of 1 plus r.
Yep. So we're going to take out a p times 1 plus r. Now you're going to be left with something. If you take out a p1 plus r from the first thing that I underlined, there you go. If you take out a p times 1 plus r from that, what are you left with in the underlined part? You're factoring out everything that's there. So what's left? No, not 0. Yeah? 1. Plus. Now, factor out a p1 plus r from the second spot. If you do that, what are you left with? Yeah, you're left with an r. P times 1 plus r times 1 plus r. How could you shorten 1 plus r times 1 plus r? Yeah. Yeah, square it. It's p times 1 plus r squared. Does anyone have a guess if I went for year 3, what the formula would be? We had p times 1 plus r to the first, even though I didn't write first. P times 1 plus r to the second. What about for the third year? Yeah.
P times 1 plus r to the third.
Yes. And how about for the year t? If we went all the way out t years, what do you think my formula would be for that? Yeah.
P times 1 plus r to the t.
P times 1 plus r to the t. Exactly. That's your exponential growth formula. So P is an initial amount. R is the rate of increase as a decimal. And T is your time. Now, for decay, you would end up changing one thing. Anyone have a guess what the one thing that would change in that formula would be? Yep.
You change the plus r to the minus r.
Right. Instead of adding a percent, you would subtract a percent. So the formula for exponential decay is P times 1 minus r to the t. questions on those two formulas? So I'll try one with you. We'll set it up. I'm not gonna solve it though because it would end up being a calculator thing, and I want to show you the last formula, which is really just a special case of growth, doubling, and a special case of decay, halving. But it's really the same formulas. So we have a town with a population of 50,000 people. It's going up at 2.5% a year. First, they want us to write a formula that shows the population, okay, as a function of time. This is exponential growth. Anything that changes by the same percentage over and over is exponential growth. What do you start with in the exponential growth formula? That's the first thing you put. Yeah.
Population.
Initial population, which here it says 50,000. Times in parentheses. What goes in the parentheses? And keep in mind, this is increasing. This is growth. So we have two versions of the formula. 1 plus 2.5%. And what's 2.5% as a decimal?
0.
Yes. So I'm just going to write 1 plus 0.025 to the t. That's the first part. Now the next part says use a graph to tell me when the population would hit 100,000. Where would you plug that in? P of t or t? Yeah.
P of t.
Okay, put it in right here. Put this in y1. Put all of that in y2. Graph them at the same time and you'd be looking for what? Henry? You'd be looking for t, and how visually, where would t be? Yeah. The intersection. So as of now, you would find an intersection. Later on, I'll show you how to do it with algebra, but that's another day. Always be careful with negatives, whether they make sense or not. So I'm going to give you the last two formulas. We're not going to go through like the explanation. Doubling is a 100% increase. That's what doubling means. It's a 100% increase. So if you take your formula, that was 1 plus r, and you fill in r as a 100%, which is 1 as a decimal, that's where the 2 comes from. So the formula for something doubling is an initial amount times 2, and the power is t divided by the length of time to double. The reason you need that t divided by in there is because if you said to me, all right, I've got a bacteria that doubles every 5 days. How many bacteria would I have after 10 days? Well, I wouldn't want to plug in an exponent of 10. That means it doubled 10 times. No. If 10 days have gone by and it doubles every 5 days, that means it's really only doubled 10 divided by 5 times, or it's doubled twice. That's why you need that in there. Okay. Does everyone have that one? And the last one is for a half-life. It's pretty much the same thing, except with half-life, your rate is 50%. Half-life just means, like, if I created something, it's the amount of time that goes by before half of what I created is gone. Some elements aren't stable. You leave them in the open air and they break down. So sometimes we explain that in half-life. Like nuclear waste has a very long half-life. It can be thousands of years. So that means if you create 200 tons of nuclear waste, maybe 20,000 years from now, you only have half of it. That's a long time. So if we need to go over a doubling and a half-life, we can do that. There's one of each in the homework. We'll go over it tomorrow. Okay, so that's homework for tonight on 268. I am going to be after school for a little bit today because I have someone else making up a test. So if you did need to make something up, you can stop by today. Otherwise, my plan is to be here on Thursday.